this scene from The Avengers, Thor is dropped out of a moving aircraft in a chamber designed to withstand the Hulk's brute force. In the simplest of terms, we can break this down to be an airplane dropping package system like we studied in class. Since the plane is moving with horizontal velocity when Thor is dropped, it will have initial velocity in the horizontal direction, as opposed to if it was dropped from a stationary high point. Because there's this velocity in the horizontal direction, it is more of a projectile system than a freefall system. Ideally, Thor will move forward with no horizontal acceleration. However, there is air resistance, so it does slow down a bit while moving. In a vertical direction, it accelerated from rest at a constant of g, which has a value of negative 9.81 meters per second squared. So the physics of this scene is wrong, as evident of Thor moving slightly back while the aircraft moves forward.
Those are some big guns.
On my command! Number 1!
Rodent, we are ready for your plan.
Hold on! Number 2! I recognize this animal. We brought some over a flame pit as children. The flesh is quite delicious. Not helping! Number 3! Command! Yeah! 3, 2, 1!
He turned off the artificial gravity everywhere but in here.
First Guardians of the Galaxy movie, Rocket Raccoon turns off the artificial gravity in the main part of the prison. Although fictional, we can look at it as a force problem. If the gravity is turned off, every guard has a force of gravity pushing down and a normal force pushing up that is created by the floor pushing up on them. However, the guards that are walking are pushing down on the floor to move. So, when the gravity is turned off, the force they're exerting down will launch them up fast, when there is no gravity to counteract it. The stationary guards will not move up as fast as they are not exerting a force beyond their weight on the ground. So, the physics of the scene is partially correct.
Les officiers ont l'air troublés. L'homme a ôté son casque et marche tout droit en direction des voitures. Oh mon Dieu! Coupez la voiture en deux! Que s'est déplacé? La voiture vite, c'est le chaos ici!
Go, go!
Scene from Iron Man 2, race cars are making turns along a racetrack. Although this isn't the main action of the scene, it's the physics we will be analyzing for this unit. Often on a racetrack, engineers purposefully add banked curves on the turns. On a banked curve, the normal force will act at an angle instead of straight up toward the sky. The equation for centripetal force is centripetal force equals r sine theta. So, increasing the angle of banking will also increase the centripetal force. The centripetal force resultant from the angled normal force can help the car move in a circle. So the physics of this scene, the background of the scene at least, makes sense with what engineers design in the real world.
Remote driving system activated.
Wait! Which side of the road is it?
For God's sake, just drive.
Okay, calm down. Woo! Let's go! Hey, look at your suit. You've been taking bullets, charging it up with kinetic energy.
Put her around the truck. Ready, go!
Black Panther, T'Challa's suit is supposedly being charged with the kinetic energy from the bullets being in motion when they hit his suit. The fictional metal vibranium uses the vibration of the bullets hitting to absorb its energy. This is a bit out of the reach of our planet's metals, but we can analyze the energy of the bullets. They have a small mass and a fast velocity. The equation for kinetic energy is 1/2 times mass times velocity squared. Therefore, the kinetic energy would be pretty high. In this scene, he uses all of the energy to create an explosion. The size of this explosion is pretty accurate considering just how much energy is absorbed. So the physics of this scene is very fictional, but somewhat reasonable. In this scene from the Avengers, Hulk punches Thor, which launches him back. The equation for conservation momentum is mass initial times velocity initial equals mass final times velocity final. This scene can be observed through conservation momentum. Hulk's fist is massive, so its mass is high. On top of that, his strength is immense, so its velocity is high too. When the fist connects with Thor, it comes to rest, meaning Thor's mass will be launched. I imagine Thor is a bit heavier than Hulk's fist, so I think he goes to the right with a little less velocity than Hulk punched him with. So, the physics of this scene is quite accurate.
Okay, let's do this right. Start mark 1/2 meter and back to center. Dummy, look alive. We're on standby for fire safety. You, roll it. Okay. Activate hand controls. You're going to start up nice and easy. You're going to see 10% thrust capacity, achieve lift. And 3, 2, 1.
In this scene from the first Iron Man movie, Tony is engineering a suit that allows him to fly through the utilization of jet boots. However, when he activates the jets, he spins and crashes. This rotational motion is caused by torque. The equation for torque is radius times force times sine theta. The radius in this scenario is Tony's body. In the case of a door, when you apply the force far away from its hinge, it moves a lot easier. This is very similar to what happens to Tony. His body then rotates. To stabilize this, he adds jets in the hands at a later point to help balance the torques. So the physics of the scene is seemingly correct.
I don't think so. It's not possible.
Darling, you have no idea what's possible.
This scene from Thor Ragnarok, Hela manages to destroy Mjolnir. She's able to do this by using the resonant frequency of the hammer. When an opera singer matches the resonant frequency of the glass explodes. This basically is what's happening in this scene to Thor's hammer. Obviously, the explosion of lightning is completely fiction, but the concept of resonant frequency makes sense. She vibrates the hammer to get the correct wave frequency, which is really, really fast. So the physics of this scene is also considerably accurate.